is Grégoire Allaire. I'm one of the organizers, also I did not that much because everything is on virtual and perfectly managed by our colleagues from Pavia, so on Roma, sorry. And so today we have two talks in the first morning session, and the first talk is given by Professor Ferdinando Auricchio. I assume that I pronounce it not completely correctly, but okay. Anyway, he's going to talk about additive manufacturing. And Ferdinando, you have 45 minutes.
Sure.
We started with 4 minutes late. Huh?
Don't worry. Thank you very much for the introduction, and thank you very much for the opportunity of talking in this workshop. I really enjoy this kind of workshops. I think is a big opportunity. So the talk is going to be on additive manufacturing, which is my last field of activities, and I will try to describe, many aspects, and in particular, I will try to show you that it's a real world full of challenges, but also opportunities. So I will start briefly with an introduction on additive manufacturing, but many other speakers already talked about additive manufacturing, so I will be really, really fast. Then I will talk about optimization, but also here I will take advantage of the previous presentations. And then I will focus on simulations and especially on immersed approach, which I feel that can be really useful for additive manufacturing, and come to some discussion of future activities, directions, and conclusions. So in the previous talk, many people talk about it in manufacturing. So really, I don't want to spend time on this aspect. The point I would really like to highlight is that under the name of additive manufacturing, in reality, there are many, many different technologies and many different materials. So you go from material extrusion, vat photopolymerization, material jetting, for example. So in the first technology, there is a thermoplastic wire, which is progressively deposited. In the second technology, there is a laser, which transforms a liquid material into a solid. In the third technology, you spray the material at the same time. While you spray, you also solidify. Or there are other technologies like the direct energy deposition, the powder bed fusion. In the direct energy deposition, you spray some powder, and while you're spraying, you go through a laser beam which melts the powder, and then once the powder touches the object, it solidifies. Or you can have a laser which basically melt a layer of powder, and then you keep depositing the layer of powders, and the laser keep melting the material. So many different technologies, which is one of the big advantages of these technologies. But at the end of the story, the very interesting thing is that you can, with this technology, there is a new world of opportunity from the manufacturing point of view, because you can really produce objects which are very, very complex in terms of geometry. So you can produce objects like the one I'm showing here on the top right of the slide, which are really impossible to produce with other technologies. So from the engineering point of view, from the design point of view, there are many opportunities, but clearly there are also some disadvantages. And the disadvantages are mainly related to the fact that this production technology is a highly non-uniform production technology. And what I mean is that basically is an additive technology. So it builds a layer after layer, and every time you build a new layer, you have a very localized, highly non-linear production process. Okay, so the technology comes with a lot of problems somehow. Okay. So is a lot of opportunities from the geometrical point of view, a lot of problems sometimes from the production point of view, a lot of opportunities again from the engineers, from the mathematicians that want to study this type of problem. So let me start from the design of additive. which is basically comes to the concept of topology optimization. Yesterday, we already saw several, and the day before, several presentations on topology optimization. So basically, the goal is you start from a domain and you want to optimally distribute a certain amount of material within the domain. So there are many different techniques on which I'm not going to discuss today. Elisabetta Rocca, for example, show some of the work we've been doing. One of the interesting points I want to point out is that once you have your algorithm and you run the algorithm and you get your so you have your physical problem, you run your simulations, you end up with your maps of colors. In particular, here you can see different colors, which means that we're looking at graded material. One of the issue is to be able not only to run the simulations, but also to construct the object. So an area where I think that geometrical reconstruction is really important is how to transform, these maps into something that you can really produce and that you can really test. Okay, so an area in which we're working is the transformation of these very nice colored maps in something which is really printable, and that's I think is a very important area. For example, this color map, the different colors means that the material has different densities. So the red is a region with higher density, the green is a region with less density, and clearly the map is continuous. So the question is how can you transform these graded, shaded picture in a real graded structure? And you can have different approach, but the way we do, basically we consider isolines, we distinguish between different regions, and we try to transform the color map in a discrete map where in each point you have a certain amount of material which is somehow corresponding to the numerical results. The very nice thing is that once you produce your component, you can do the experiments, and that's something that we can do in the lab. And that's also a great opportunity because before 3D printing, we were just doing numerical algorithms, simulations, and things like that. But now with the 3D printing, we are really able, we somehow construct in our lab a production facility. So we're really able to produce components and to do the experimental tests on these components. Okay, and here, for example, you can see a very interesting result, what I believe is a very interesting result. So these two components share the same initial geometry. The one on the left is optimized, the one on the right is non-optimized. The amount of material on the two structures is the same. So here we distribute a certain amount of material in a uniform way, and here we distribute the same amount of material in a non-uniform way. So we get, these fancy supports, we get a hole in the middle, and so on. And clearly the distribution of the material is optimized for this loading condition. And then you can do the experiments, and very interestingly, you can see that, for example, for the same amount of displacements, the optimized structure is incredibly, let's say, is much stiffer than the non-optimized. So really, the optimization schemes really work, and you can really see these also from the practical point of view. So a key point is to transform these color map in real object, and this is something that you can do in 2D, but it becomes even more interesting in 3D, because in 3D, when you do the optimization, we were looking also yesterday, clearly you get very complex geometries, with holes that goes inside the structure, very, very complex geometry. So you can see here the results for a 3D cantilever beam here, and for a 3D bridge with a uniform load. So the results from the optimization is extremely complex. So the question is how to transform these in a structure that you can really 3D print. Okay. Another word of opportunity that comes from 3D printing is the fact that when you do topology optimization, you don't know exactly where the material is going to distribute. So, for example, here you can see a square where we distribute a certain amount of material. This is the optimal distribution, but clearly this optimal distribution is unknown from the beginning. So the question is which mesh you should use. So you can start with a very fine mesh from the beginning, or you can use some sort of adaptivity scheme. So you refine only where you really need your finite elements. So adaptivity is something that really comes into the picture when you deal with optimizations and so also with 3D printing. So here you can see some result of adaptive schemes combined with topology optimization that Elisabetta Rocca was showing, and some isogeometric approximation. So adaptivity is another area of big interest. Okay, but let me come to really the most important part of my talk, in which I will discuss not optimization but simulations in terms of process and product simulation. In particular, process simulation is extremely important, and here the goal is really to show you that immersed method can be really effective. Why immersed method can be very effective? Because the standard way that people approach simulation for additive manufacturing is a very iterative scheme, is a highly iterative scheme, in the sense that you start with the geometry, you come up with the geometry maybe from a sort of optimization, then you mesh your geometry, but once you mesh your geometry, then you want to simulate not only the optimal distribution, but you want also to simulate if the distribution that comes from your topology optimization is optimal in terms of construction process. So you want to take your geometry and you want to do the simulation of the additive process, of the construction of the component. And if in the construction, like we were looking at yesterday, some overheating region, if the construction is non-optimal, then you need to go back and change your geometry and then generate again the mesh and so on, do this in a very iterative schemes, which is really time consuming. So the idea here is instead to use immersed technology, which somehow don't change the mesh, in some sense, don't change the mesh during the simulation. So basically the idea is that if you need to do like a simulation of a component which has this geometry here on the top left, you immerse your geometry, your physical geometry into a larger domain, and you simply mesh your larger domain, okay? And you can use in your larger non-physical domain, for example, a very regular mesh. So then the point is, how can you take into account the geometry? And one of the methods we are exploring in collaboration with colleagues from the TUM University is the finite cell method. This is a very interesting technology where basically you convert let's say, the immersed non-fitting geometrical method in a fitting method through the introduction of an accurate integration formula. So the method is geometrically non-fitted in the sense that the mesh does not fit the physical geometry, but somehow you make it fitted in terms of integration points. So if there is a region where the boundary has a slope, you can describe the slope locally refining the number of Gauss points. Okay, so then you have Gauss points which are outside the physical domain, which are weighted 0, and Gauss points which are inside the physical domain, and you really weighted with 1. Okay. So this technology is very interesting because basically what you refine when you also have the additive construction, you don't refine the mesh, so the mesh is fixed, but you refine progressively the integration rule, okay? And here, what is also interesting is that you can easily play with the different level of approximation, in the sense that you fix somehow the background mesh that's fixed, that's given, but you can progressively increase the number of Gauss points depending on the layer that you activated. And the layer can be as small as a real powder layer, or it can be, you know, like a group of powder layers, and so on. So you can really, you're very flexible because the geometry is fixed. And again, you choose how many layers of non-physical, how many non-physical layer you can progressively activate it. And with this technology, we do two types of simulation. We do melt pool simulation. So we really, these are, let's say, a mesoscale simulation. So we are in the order of microns, of tens of microns. And we really want to evaluate the movement of the laser and, you know, the melt pool shape. Or we can try with exactly the same technology to simulate part scale components. So the whole, the whole pieces, and now we are in the range of centimeters in terms of simulations. And the goal in particular of these sequence simulations is to be able to reproduce effects like these. That's an experiment that unfortunately we did in our lab. We have a metal printer. We 3D printed a metal plate with a bunch of components, and there were so many components and so many residual stress that the screw that were tying the plate to the machine broke, such that, you know, the plate at the end, you know, bent completely, and so we had to stop the production with some economic loss. So with this technology, again, we can produce simulation at the melt pool level. The way we do it is that we combine a thermal model with a mechanical model, very simple thermal model. We try to be as simple as possible, otherwise, you know, you don't get results. And that's the simulation that we are able to perform. You can see, you know, nice colors for the thermal part, which then feed, you know, results into the mechanical simulations. Since the model is very simple, there is always a question or how reliable, how effective is your model. So we took advantage of some bench tests that were performed in the state and NIST, and here you can see some very interesting results. So basically, these are ex situ measurements. So you can see a shade where basically the specimen. So there was the experiment, then the specimen was taken and cutted, and you see the dimension of the melt pool after the process, and with the dashed line, the numerical result that we obtain, and clearly there is a good match. And also we were able to do some in situ measurements between the melt pool length and the model melt pool length, and, you know, the two things seems to match quite well. Then once we are quite, we feel that the model at the melt pool level is quite reliable, you can do also simulation at more larger scale, which is the component scale. And again, here we have a very simple heat model with a mechanical model, and the two models are coupled. And using these, you know, we can do simulations like this one, where basically where you see the colors growing up are because we model, you know, the activation of single layers. So that's the mechanical stress, and then we're also able to simulate, you know, the removal of the component from the plate and the bending, which is something that in reality you don't want it, because you want to start from your initial geometry and then end up with an optimal geometry. But in any case, we are able to, you know, in a quite reliable way to do this kind of simulations. So this is the finite cell method, which is one first immersed method that we explore. But at the same time, we're exploring a different technology, a different immersed technology, which is as follows. So the goal is, again, to construct an object of complex geometry. So this is the final, in green is the final object that you want to build it, and you want to build it in an additive way. So at a certain instant, you have this region which you already built, and there is a region which is, it will come in the future. And at this time, you're working with this domain, and in particular, you're building this specific region. So in the physical domain, you have basically a region where you deposit the material. In general, you have a highly nonlinear phenomena, and you have a region where your phenomena maybe it's nonlinear, but it's not highly nonlinear. Okay. So the point I want to make is that from the computational point of view, we have many difficulties. One is this evolving domain. So the domain, the physical domain where you need to run your simulation is evolving in time. Not only that, but in the physical domain at a certain time instant, you have a region where the phenomena is highly nonlinear, and you have a large region, in general, large region where your phenomena is not necessarily too high nonlinear. And this region is important to understand what's happening in the small region. So you always deal with the two-scale phenomena, two-scale range of effects. So the idea is to simulate, again, this problem with an immersed method. So we introduce a global coarse mesh, which mesh the whole domain. This global mesh is divided in a part which is non-active and a part which is active. So in the global mesh, we distinguish between the active and non-active region. And then in the region which is active, we don't have only the global mesh, which is, let's say, the crude mesh, but we also introduce an extra mesh, which is a very fine mesh. So also from the computational point of view, we have a global evolving domain, and we have a local and a global mesh, and the local mesh is moving in time. So the global mesh is fixed, but the region which is active is changing, and the local mesh instead is moving in time. Okay. Now, with all this concept, the idea is how can we transform our model, in something that fits with all these concepts. And here you can see the development of what we name a two-level method. That's a collaboration with Alex Viguerie and Silvia Bertoluzza, and comes from a previous work of Silvia Bertoluzza. And the idea, basically, here I'm showing the concept on a toy problem. So let's assume that we have a thermal problem on a domain like this, and inside this domain, we have a region B. So we have a region A and the region B, and for example, we have different constant in region A and region B. And we want to solve the thermal problem in A and B with the standard boundary conditions, the coupling boundary conditions between the two domains. Now, the idea is to transform this problem in a global problem and in a local problem. So the global problem is defined on the whole domain. And when it means the global domain means that I don't see the inclusion. And in a local problem in which I see only the inclusion. So I transform this domain, which has two regions, in a problem which is global, which I call omega plus, in a domain in the total domain, which is omega plus, and a problem which is in the domain, in the local domain, which is omega minus. And the standard equation I want to solve are the classical heat equations. So I can transform my heat equations, as I was showing you, in something which I solve on the local domain. That's this part. Then I solve the problem on the global domain, clearly have some coupling terms between the local and the global problem, and then I also have a relaxation steps. And clearly this is also, if the regional problem is linear, I need to introduce some iterative schemes in order to obtain convergence numerically, but there is the opportunity also to do a lot of proofs from the theoretical point of view, and you can see that iterating you get the solution of the regional problem. Here I will show some numbers on a very simple problem, a 2D problem. That's the problem. So I see, let's say, a lower part of the domain, which is domain A, an upper part where I could include some nonlinearity, omega B, and then an heating just from the top. And I split this problem in a global problem on the whole geometry and just a local problem. And here you can see some results, which I think are very, very interesting. And this result, what tells you? It tells you, basically, I'm fixing, for example, if you look at the blue curve, I'm fixing the mesh at the global level, and we are refining only the local mesh. And refining the local mesh, basically we reduce the error. So which means that if the nonlinearity is only local, we can really refine only locally, and we are converging to the right solution. So if the nonlinearity is just local, we can do just a refinement at the local mesh. Here you can see a more interesting simulation from the engineering point of view. On the left side, you see a temperature profile. So it's like the laser is moving from left to right, and then the domain is evolving. And on the right, you can see instead the material profile. So the phase transformation and what's the geometry that we are building. So we can extend the previous technology to something which is more complex, okay? So this is regarding process simulations, but also product simulation is very interesting. And here I'm showing two different area of activities. One, it's more, let's say, research oriented, and the other one is more industrial, toward an industrial collaboration. In terms of research oriented, we are looking at the lattice structures. So with additive manufacturing, it's very easy that you want to do, when you want to make a light component, so if you want to distribute a material with low density, you end up doing a very tiny structures inside the material, and you try to make this structure very, very small. What's the issue? The issue is that when you make the structures very, very small, very easily you end up with the geometry which is in the range of the technology precision, okay? So the powder dimensions in the order of few tens of microns. So the laser spots is in the same order, and what people usually try to do is really to do these struts, this geometry which are in the range of few tens of microns. So when you do these kind of things, you start to have some problems. And what are the problems? What we realize, which is something that's known in the literature, if you take a structure like this, so if you design with your CAD a structure like this, and you do the simulation of a geometrically perfect structure, you get some type of response. Once you construct your component and you do the experimental test, you get a very different response. So here you can see, prediction with the perfect geometry, and that's the behavior instead that we really get experimentally. And the issue, once you start to look at things, the issue is very clear. The issue is that when the picture I'm showing here on the right is a picture taken from a micro CT of the component. And if you see in details, you will see many spots where there are defects. And these defects, are very close in terms of dimension to the dimension of your typical structure element. So when you do very small structures and you have defects of these types, clearly the real structure is very different than the ideal structure. So you start from a CAD, so you have a geometrically idealized structures, you build it up, you can measure the real structure, but the real structure is completely different. So the question is, how can you do this simulation? Because this geometry, again, is a very detailed geometry. It's quite complex to describe. If you want to do if you want to use a fit technology, it's really complex because the geometry is very difficult to follow. So the idea that we had was again to use the finite cell method. So we immerse this geometry inside a larger domain with a very regular mesh, and we we took into account the real geometry with refining the integration scheme. And what is very interesting, for example, is this picture down here. For example, this is for the 3-point bending test. You can see that the mechanical behavior, the predicted mechanical behavior from the perfect geometry, is this, for example, this is this result. The experimental is this one. the blue one, and the predicted with immersed technology is this one. So if you compare experiment with what you are able to predict with the perfect geometry, you are not predicting the real behavior. But if you predict with the real geometry, you can do, you can really obtain, you can really be very close to experimental data. But to do this, you really need a method which is very flexible from the geometrical point of view. Otherwise, it's impossible to take into account, the complexity of the geometry when you produce these components. Another area instead is the simulations, the product simulation in terms of support to companies which are using more and more additive manufacturing. And here I show you a very simple example, but which was extremely interesting. So this is a Florentine Lilly geometry. It's just a logo that the company asked us to produce. So it's a very complex geometry. Here you can see the geometry with the support that we produce it. And the first time that we produce it, we get a very funny, strange behavior. Basically, there was a misalignment between the bottom part of the component and the top part of the component. And this was, clearly looking at the production was clearly due to some overeating in this region up here. So the idea is that you can do the simulation of, and here we're using commercial codes, you can do the simulation of the production process, so you can predict this misalignment and you can compensate your geometry. And once you compensate your geometry, you're going to print, a geometry which is compensated, which originally has some sort of negative misalignment, and at the end of the production, you are able to correct your and to obtain a component which is, as a final component is much better. So let me try to come to the conclusion. And in terms of conclusion, I really want to, somehow change a little bit direction and show you that 3D printing is really a world of opportunity. I think I show you that's a world of opportunities in terms of mathematical aspects, in terms of simulation aspect, in terms of lab perspective, because you can really produce your components for your lab. What is really fascinating is that it really brings you more and more in contact with companies. And here I'm showing you some of the technologies that we are bringing in our lab. So now in the lab, we have a metal print. These are just few of the technologies we have. So that's a metal printer. This is a jet fusion from HP. That's a polyjet machine from Stratasys. So you can really come up with different technologies. Each single technology has own benefit and problems. And recently, we're also able to acquire a subtractive technology, so we can combine now both additive and subtractive. Here is an example of something that we developed with the company. So it's just, an object, a metal object. But the very nice thing is that we produced the component additively, and then we refined it. We did the final working subtractive. And the very nice thing is that also to do the subtractive, we produce some of the component with another 3D printer. So 3D printer really we use not only to produce the metal component, but also to produce some component that we use to do the final work. You can see here, complex geometry that we are able to produce with different, some of the different technology, the metal machine on the top, the nylon machine, the HP on the bottom, quite complex geometry. And this opened the doors to even more simulations. For example, here you can see another very interesting collaboration that we're doing with the coffee maker machine. And basically, we're optimizing the thermal distribution inside the component where they put the coffee, because you want to keep it to a uniform high temperature, so you can really bring topology optimization to the real world. And really, and this also opens, all these activities, all these facilities open the door to even more activities. For example, here you can see our activities in collaboration with doctors. We have a lab in the hospital now where we start from CT images and we reproduce organs with different mechanical features. And these mechanical, these organs now we place within reproduction of the complete part of the human body, such that doctors can really practice surgery on reproduction of the human body. Or there is a very interesting collaboration with some colleagues again from the medical world in terms of bioprinting. So the 3D printing of gels with cells in order to observe proliferation of cells. Or there is a collaboration with colleagues in the terms of 3D printing of concrete components, so large components, or very, very, very interesting collaboration with other colleagues in order to do 3D printing of devices with change shape in time, for example, with temperature or with light, in order to make active components. So let me come really to the conclusion, and the conclusion I think is very simple, because I can only thank, because everything I show clearly doesn't comes only from my work. In reality my work is really minor, but I have many wonderful collaborators which are part of all these activities. So Massimo Carraturo, Stefania Marconi, Gianluca Laimo, Alessandro Reali, Michele Conti, and Simone Morganti here, but clearly there are many other co-worker, and here are all the members of the Pavia teams. And I hope, as really final conclusion, that I show you that 3D printing is really breakthrough technology with a lot of opportunities. Thank you very much.
Ferdinando, thank you very much for your very nice talk. I was very happy to see that you are working on real problems of importance, like improving coffee machines. So I guess it's not in Italy that you really need to perform this research, you should export it to the USA, let's say. Good. Anyway, it's time for question. Yeah, there is a question by Daniela Di Sarafino on the chat, so please ask your question maybe.
Yes, I show up. Okay. Good morning, everybody. It's just a curiosity. Thank you for your talk, which is was very interesting. And you talked about industrial productions. And usually it seems to me that all the devices that you build are pretty small. What happens if you have, I don't know, in your experience, have you ever had site constraints, in the sense when you produce something? I think also about coffee machines, for example. Are you allowed to use any sites you want? In the sense that if there are constraints in the sites, how do you deal with them?
So in terms of industrial productions, the let's say industrial 3D printing machines are today in the range of 30 centimeters. So in general, you can produce object up to 30 by 30 by 30 centimeters, okay, more or less. Okay. These are the standard, the most standard technology available. You can go high with the higher dimension, but the machines really become very, very expensive. Or you really need to change technology. So you need to work with like robotic arms. And there are some areas where you can print, for example, for concrete. People work with special machines, so you can really print big components. For example, there is an Italian company now that 3D printing like a boat, or there are companies that are printing small houses. So there is a lot of research on big components. There are also machines, if you talk about metal printers, machines that deposit a wire and melt it while it's depositing. And these machines in general are much, they can produce much larger components. But the standard, let's say, classical are around 30 by 30 by 30 centimeters. And clearly, if you want to produce a component with this box, sometimes you have constraints. Yes. Still 30 is not, I mean, it's quite large, I would say. You can produce a lot of things. And sometimes you wanna go also much smaller. There is also very interesting technology on what's named the microfabrications. Unfortunately, we're not working in the area. I hope to move in the area soon, where you wanna do components which are, channels which have dimensions of like 5 microns. And then the the technology is slightly different. It's like stereolithography or other things, which is also very, very interesting. So dimension is always an issue.
Okay.
I don't know if I answer your question.
Thanks a lot, because I'm not from this field. I was just curious to understand how much dimension can affect your simulation and the actual possibility of producing those devices in a let's say in a production context, because in the end you have to build something.
Yeah. You can do a lot of things. Clearly, you always want to do more.
Okay. There is another question by Marco. Marco, please ask your question.
Yes. Thank you. Thank you for the very interesting talk. It's very inspiring. I am particularly interested in your contributions regarding process simulation. I see that all of your techniques are based on regular meshes, which in 3D are made of, well, voxel-like cells, right? And as you said, this requires to refine near diagonal surfaces, and you also shown that adaptivity is necessary to have enough precision near the melting pot. All of this makes perfectly sense, but I wonder if the implementation of the whole machinery would be simpler by using tetrahedral meshes instead of voxels. Well, these would naturally align with diagonal surfaces and is inherently adaptive as you need. I say this because we are currently working on slice conformal triangle meshing, tetrahedral meshing for additive manufacturing processes. So just to know your opinion on that.
Yeah, it's difficult to give a real answer because it's again there are so many opportunities in this world. So we are following this type of immersed technology, let's say, for also I'm really honest, by chance, in the sense that you work with colleagues. Some colleagues develop some technology, so you really push that technology. For sure, it's not the only technology. So this technology seems to be very nice and very flexible. Especially this finite cell method, which is really has been developed in the years from the colleagues from the Technical University of Munich. So that technology seems to work really, really well, and it's being very effective. Clearly, other technology like local refinement and adaptive refinement on the fly, is also an area where there has been so much work and so much experience that for sure there are many chances also there. I'm not an expert on that, so absolutely I cannot compare. The thing we can do, we can try to work from the scientific point of view, and we can work on some common geometries and try really to see the benefits and the non-benefit of both approaches. As usual, every approach has good points and bad points. I'm sure also our approach has bad points. So the only thing we can do is to work on a common geometry and try to compare things. In fact, this comes also to something I want to say, but I didn't say. I show you the machine that we have, not only because I'm really proud of them, but because that's really the beauty of having the machine, is that you can produce components, and we're really open and willing to do components and to start a collaboration also thanks to this technology. So it's a such intriguing and enthusiastic area of activities that I'm really open to collaboration. So we can collaborate on this kind of geometry aspects, or on producing components and see how really different tools behave. So unfortunately, these virtual conferences are very nice because you do from home, you do you don't travel, but the bad things is that you don't have a real coffee break where you can talk and start collaboration. So I'm really open to collaborations, especially with this community. So please just send me an email and we will try to share more in details informations.
Yeah, I will. This is very
Thank
interesting.
you very much.
Can I add something here?
So there is a question. I think, Mathis, you raised your hand, so maybe you have a question?
Yes, thanks, if there's still time. So
Yes,
thanks
of
for the great talk.
Thank you.
Very impressive to see this whole range of activities that you have. I have a question that was triggered by the lattice structure that you showed.
Oh, yeah.
Because yeah, I look at it from the viewpoint of design. We observed similar things when we printed very tiny structures, flexures, that actually the performance was quite different from what you would predict.
Yeah.
And so it's impressive that you can mesh and predict the performance of the lattice with all the defects. But the problem I have is you don't know the defects in advance.
Absolutely.
So how do you have ideas how during the design phase maybe you can already take this to some extent into account?
There are some colleagues that are doing stochastic approach. So you introduce some randomness in your geometry, which we haven't explored so far, but I know that there is a lot of literature in these directions. I mean, if you really want my point, because we're working with companies, so if you really want to produce a real piece, forget about lattice. I mean, but that's clear, if your technology precision is 40 microns, I mean, your smallest details can be, should be 100 microns or more, no question. So if you really want to produce components, forget about lattice structure or very small lattice structure. But if you really want to play with lattice, you can introduce some sort of randomness in your defects, distributed defects, but it's something we haven't explored at all so far.
Okay, thanks. That's good advice.
Yeah, but this, I mean, as usual, this lattice. So if you see mechanical response, okay, you say, I'm really afraid. Clearly, these small structure and these defects can be really benefit in terms of post-critical behavior, in terms of fatigue. So again, there is always you lose something, maybe you gain something, but the matter, as you say, is to control and not to take CT scan of each single component. So
not to rely on luck too much.
Yeah,
yes.
Exactly. But that's an interesting area of activities we hope to explore in the future.
Okay, thanks.
Thank you. I will continue on Matthew's question, because I mean, a lattice, when you don't orientate its microstructure, it's far from being optimal. So I'm wondering why people are so much interested in lattices if you take a simple geometry like this and don't orientate it, because then, I mean, if you do optimization with such a structure, you will get no lattice at all at the end of the optimization if you don't orientate it.
No, that's a very good point, and some people are looking at specific oriented lattice, but we haven't done anything about that.
Okay.
But that's an excellent point. Absolutely.
It's just a remark. It's just a remark. Sure. Then I have a question, because I was very much interested by your macroscopic simulation. So for example, you simulate the heat equation to compute the thermal stress, so at a macroscopic scale. So I have a naive question, not so naive question. How do you find the material properties, let's say the conductivity, thermal conductivity of the powder, right? And my second question would be, is it really important, or should you do some calibration, by comparing with some experimental measures in the end? Because, how do you find those material properties for the powder, for example?
Okay, so when you do the macro scale, you're talking about macro scale.
Yes.
Okay, when you do the macro scale, the thing you can do some micro simulations, on a components like these, for example, so on a multiple scan, and try to get some of the features. But clearly, going from the micro to the macro scale, it's a big jump. So there is no clear, no clear and unique step in the way you do this thing. That's a sort of recipe, and usually the only way you do it at the end of the story is you calibrate your technology, you prove, you validate your technologies on standard benchmarks, and once you have it, you say, okay, I can extend it. But that's a clear limitation of the whole process, no question.
Okay, so for example, you show this kind of honeycomb comb structure, where you have this deflection after you cut it from the base plate.
Sure.
Are you, for example, calibrating with this experiment? Because to tell you the truth, that's what I do with some of my industrial colleagues. So that's the way we calibrate on some very crude.
You mean these things here?
Yeah, for example, this one, but this was about lattice, but the other one, the comb where when you cut it,
in this one, well, it really depends on the simulation we are doing. I mean, because for example, this one, no, we did it for this one, that just in the elastic range.
Right.
So here we did only the simulation taking the material properties from the production company, which we validate with experiments, but these are basically the elastic moduli from the production company. In other simulations, which are at the micro scale, things like these, we look into the literature and we try to learn from the literature experimental data, but we don't do measurements on our own. That's far away from our ability really to measure these things. Also, if in some of the simulations, for example, these there is a lot of experiments from the bench activity. So here you can, there are many results that you can start from. So okay. It's a slippery area.
I agree. I was interested to have your opinion on that.
Absolutely, very slippery.
Are there any questions? Okay, so I don't see anybody raising hands. So thank you very much again, Ferdinando. And so I think we can move to the next speaker. So the next speaker is Auricchio-Breuss from the. Are you here? Are you?
Yes, I'm here.
Just yeah, you're here. Are you able to share your screen?
I hope so. Should be this one.
Excellent, we see it.
Okay. I hope I can make it.
Talk about big. Mathematics for printing metallic structures, and you have 45 minutes. We are starting with 7 minutes delay, but
yes, no problem. Okay, so let me start. First, I have to maybe apologize a bit for the title because it sounds very bombastic. The reason is that I wanted to be a bit fuzzy in advance when the talk was announced. And well, there's much ongoing work, but then I decided also a little bit during the conference to switch a bit the objective. Yes. Because we share here more or less two communities, one from 3D vision, one from 3D printing. And my background is more from image processing, 3D vision, but I am indulged in a project with 3D printing. Yes, it's not so long ago, but it is a real collaboration here within an European funded project. And done together also with colleagues from mechanical engineering and with other professors here in mathematics at the Brandenburg Technical University in Cottbus. And this is relatively fresh. So I've decided to go back a little bit so that one may have an idea how 3D vision or techniques from 3D vision image processing may be useful in 3D printing. And because it is more of the beginning, it is not like highly polished results from many years of research. So if you expect something highly complicated, this is not in my talk. Okay. So because more or less it is a collaboration with my colleague Markus Bambach from Mechanical Engineering and with Armin Fügenschuh. He is a professor of mathematics. Many people are involved. So the talk encompasses, as simple as it is, more or less, joint work with a number of people that you see here. Yes, and I, of course, acknowledge this greatly. So, metallic structures. I hope you see my screen conveniently.
Yes, we do. We do see it.
Very good.
And your mouse, too.
Okay. And so the starting point.
Excuse me, can you insert the full screen?
Yes, there is. Just a moment. So I try. Just a moment, please. I'm not so familiar with this. Where is full screen?
There was Folk Build Menus, you know, something like this.
Pardon?
Yeah, Folk Build Modus.
Full build modus, yes. I'm searching for it.
I don't know German, but I think this is the right.
Yeah, full build modus. It's right.
Below. Control L.
Try Control F.
Yeah.
Yes. Excellent. Thank you.
Sorry. Okay. So let me also. I have for me personally, a little bit irritating line here. Okay. So the starting point of our investigation was this wire arc additive manufacturing. So everything I tell you is not necessarily limited to this. So it is about printing metal, printing hot metal. So you can also imagine having a powder bed and a laser going over it. Okay, so but we started with this wire arc additive manufacturing. And so we see here on the left the robot. And the robot has in it a wire which is melted at very hot temperatures, several hundred degrees. And then it is put on this manufacturing plate. And so you can put together pieces of material. Yes, and of course the material that is when it is put together and assembled, the final quality of the workpiece that is achieved is related to the cooling process and to the heat that is distributed during the process. And this will be also part of my talk. But I will speak also about the geometry that one may do in this context. Yes, because when you print metal, it is desirable since the workpiece that you have finally has a certain weight, to reduce the weight, but still remain as stiff as possible. Yes, and I will speak more or less about two simple approaches borrowed from image processing techniques that could be useful for that. So just a moment. Okay. So so this was an example workpiece that we had a look on. We also printed it and investigated, but here I just show it because of the nice picture. So, so what was the initial problem? The initial problem is, at least when we were starting discussion with the guys from the engineering department here, that we have an outer shape of some structure like this horseshoe, for example, and the structure is non-convex most often. And you want to make it stiffer, not have just the outer shape, but you don't want to print it fully. You want to have some certain supportive structures in it. So like these bars here that are printed in addition. And the usual way is that you have, when you look at the printing process, that the engineers have some printing software, and there are some proposals that are made in order to put in the supportive structures. And it is relatively simple, or you would do it by your own, by a good engineering intuition. The question is, can you do it in a somewhat easy to do way? Yes. which means not hours of many simulations, but something that is at least better as most of the intuition that you can have, and which works like this. So you just push the button and you have it, and you can easily do it. Yes. So the aim was to determine some structures of such high strength to weight ratio, and you want to do it in a quick and reasonable way. Yes, and adaptive to the structure. Yes, of course, one can always put in some structures like you can do from scratch and try to fit in, but it is not certainly adaptive. And the other point is you want to have a certain control over the process. So you want to have a control over the weight of the material that you want to deposit and so on. So this is an important thing for the engineering process, not just the computation and not just having some fine recipe, but you also want to have this kind of control over it. And of course, you want to optimize the printing process. And the printing process depends highly on the temperature distribution. This is something that I aim to touch also here. So the contents of my talk are two ways. The first is about some simple, so-called simple ways to introduce some stability enhancing structures into printed objects. And well, we have witnessed many beautiful talks, many from shape optimization, topology optimization, and some others from 3D vision. And I try to give maybe some outlook on how one could borrow ideas, some simple ideas in my talk. Okay. And the second stage, which can be always built on top of the first stages, basically, is how to compute an optimal printing path and how can you optimize the process of printing. Yes, because the process is very important for the quality of the material. So this incorporates many mathematical techniques and models. Well, originally I wanted to build a bit more about this and what we had, but I abandoned it a bit. And but I will also try to introduce you the main ideas that we already really used. So this is kind of a sketch of the complete pipeline that I'm speaking of. So we have given a geometry here in this simple sketch. It's just the initial square, okay? So we want to build some reasonable structures, and then you have, then you see here some graph-like structures of these supportive structures that you can build. So I'm speaking of something that is at the moment just two-dimensional and then can be put layer-wise on top of each other's. But all of the recipes that I'm speaking of can be extended to 3D. Yes? So there's no limitation. Yes? It's just that what I can really show with confidence is this here. Then after one has extracted the graph of these structures, so the graph consists of the boundary plus the supportive structure. So you have here in the middle, you have some nodes and you have edges that combine the nodes, and you have a graph, okay? And then when you really print with a laser or with a robot that I've shown you, you start at some edge and you start at some node and you go along the edges. And then the question is, in which way do you do it? Yes, and how fast do you do it if you want? But the way is especially important. And here, for an example, you see you start here at, somewhere here, then you go down and then to the middle, and then you come to one node where you come from the way number 15, from the way number 3, and then you see the way you print also depends on this graph structure. Yes, because when you have in the middle these nodes where you have 3 edges and one node, you can go 2 times in, but you can only go 1 times out, for example. So at this point, when you just go on each layer, each route just once, yes, What you do, of course, is you can print double ways. Yes, sure. Yes, so this can be also incorporated in a mathematical model. But basically, then you have to jump. Yes, and this is also not good in many manufacturing processes if you cannot go along some path, a continuous line. So you want to minimize these jumps as much as possible. And it is also, of course, a matter of printing time. Yeah, sure. And so the question is how to build these optimal paths. Yes, taking into account the heat that is diffused during the printing process. And I will tell about this a little bit later. So this is more or less a sketch of the complete pipeline at hand of an example. First, building some reasonable geometry for your problem, then building the graph, and then do the optimization. So one interesting structure that we have also had a look at in some parts of some talks, at least sketchy, are the honeycombs. Yes. So when you go into literature, you find also some justification of this. And of course, you can try to have a certain structure like this and put it into your geometry, and then you have saved some material, and still you still one has the idea somehow justified. One can say that what you get is not a bad thing from the stiffness point of view. But the question is, how do you do it when you want to do it computationally? Because when you fit in, you have no control, or not very much control over the material that you spend. It is not certainly adaptive to the geometry, because when you may have some parts that are more subject to some stress from outside when you want to do with it something. And so it is a nice basic idea, but how to explore it and how to do it in a reasonable way for some geometry. And this is related to somehow caught our attention. And also the engineers in our department were quite open to this idea to do it. And the question is how to approach this from a mathematical and computational point of view, and to make it really kind of a flexible design tool that you can push the button and do it in a reasonable way, having some control over the output and so on. And the fundamentals of it, or the basic idea that you can explore, is the so-called Voronoi tessellation. Yes, I'm pretty sure most of you know it from somewhere. So, but let me explain still a little bit. So what you're doing is we just take here the unit square, and we put in some seed points here. I think these were 20 seed points, and then you build up the Voronoi tessellation from it. So when you always look at pairs of points here on the right picture, then you see that the boundaries that here that are built up are simply the boundaries that share the same distance to the adjacent points. So this is the way how the Voronoi tessellation is built up. When you look here to the right, it is not kind of a nice honeycomb-like structure that you may expect. So when you go back here, it is somehow clear that you have equal distances, but the points that have been used to generate maybe such a honeycomb structure, they were more evenly and better distributed than this here. And even in regions where you have some equal distribution, it does not look too nice. But there's a modification of it, and this is the centroidal Voronoi tessellation. And in this kind of specific Voronoi tessellation, the generators coincide with the centroids, which means the barycenters of the cells that are generated. And what you can have in addition is that you can impose also a kind of a stress map or some density of whatever you want. So this is a design function that you can impose. And this modifies the distribution of your and the shape also of your Voronoi cells. So let me take here as an example. So this was the Voronoi tessellation, not centroidal from the last slide, where everything was looking not so uniform. And then you put in the technique for the centroidal Voronoi tessellation, and I will go in fact into some more details about this. And here in this image, it's still a centroidal Voronoi tessellation, but here at the point 0, 0, at the origin, you have put in a higher density as an underlying weighting function, and then you see that the Voronoi cells are still looking somehow like an evenly distributed shape, yes? But they are more concentrated than this. So you get some design freedom. Yes? And of course, the other part of the design freedom is how many generators you put into it in order to construct Voronoi cells. So this seems to be not unreasonable. Yes. So when you look at the mathematical construction of it, so let me stress, this works automatically. So you give the boundaries, give the generators, and everything else works automatically. So, but what you need to do in order to find this, and let me remember just this horseshoe that I showed from the beginning. So the geometries that you wish to address, in general, they are non-convex. They can have, especially in 3D printing, we have observed this many times, that they can have many shapes. So when you really want to make this a tool that is versatile, you have to make the algorithm versatile. Yes. So, and when you look at the basics of it, it is in fact not so easy as it seems anymore. So when you look, first of all, the basics here itself at this slide are still easy. So when you have a centroidal Voronoi tessellation, this corresponds to an energy minimization. So this energy that you see here, it looks quite simple. So you have this density function rho. You have the generators, and you minimize on the corresponding cells. And then you have the Lloyd's algorithm. And the Lloyd's algorithm is an old algorithm from 1982. One can also prove convergence and many other things for Lloyd's algorithm. This is all classic applied mathematics. You iterate the following cells. So you give in a certain number of these generators, xi, and then you generate the Voronoi cells. And then, given these Voronoi cells, you replace the generator with the center of mass in the Voronoi cell. Yes? And then you iterate the process. You repeat it. You take these as a new generators and so on, and you do it until convergence, whatever convergence means. So, and when you look at the algorithmic approach, there are, as usual in image processing, at least, it is very usual, there are many ways that you can go. Yes. And building up a Voronoi tessellation, okay, you can also quickly do it in MATLAB. But when you do quickly in MATLAB, then what do you get? Yeah? And when you look at the basics of it, there are basically two main approaches in it. And the one is here sketched on the left, this geometric kind of optimization. It seems to be at the beginning very easy to do and deploys a Delaunay triangulation. It is also a classic algorithm, and this is also mainly applied in MATLAB. And then you have the PDE-based approach, yes, which relies, because you have geodesic distances, yes, imposed with some weight over it, and it relies on the Eikonol equation that we have also witnessed many times. And of course, you can discretize it with many well-known schemes, find the differences, semi-Lagrangian, and so on. So, and which approach is now better for finding centroidal Voronoi tessellations for such a potential application where you have fancy structures? Yes, because you don't have convexity or whatever of your structures in general. And then you realize when you go look into these details that these approaches are really very different. So when you look at the and I will explain a little bit about this. So this caught our attention because we thought when you really want to make this a reasonable tool, we need to have really a look at the fundamentals of it and try to understand really what are the algorithms doing and what is the better way, and how to set up the computation in a reasonable way. Yes? And I will try to explain a little bit about this. So let me explain a little bit about the geometric optimization, how it works. So very easy. So you put in these generators, then you build up the Delaunay triangulation, build up triangles, you build up the circumcircles, you take the centers of these circumcircles, and then these centers generate the nodes of the Voronoi tessellation. Yeah, no problem. Then comes the boundary handling. Yes. And the boundary handling, when you really want to have, when you want to consider your boundary, what you need to do with this geometric approach can be seen here in this simple figure, because what you need to do is you have to mirror the nodes at the boundary, the computational nodes that you used here, the red points. Yes. And this can be problematic. First of all, what about curve boundaries? Second, what about highly non-convex domains? Yes, imagine you have two branches that are very close to each other. You mirror some generator. Suddenly a generator lies inside the other boundary or very close to it, and everything mixes up. Yes. So such things can be resolved somehow, yes, but it gets very, very tedious. The other thing that you notice here when you look at this, you don't have a grid. Yes. When we speak about the PDE-based method as the alternative, we want to solve the PDE numerically on a computational grid. There's no grid structure here. So just the points, the nodes, some triangles that you build up, and very easy computations in principle, and no need to speak about grid refinement or whatever. Yes. So this is the principal advantage of this. The other thing is when we apply Lloyd's algorithm in order to do it, and then we try to start shifting along these points, then the question is, what means convergence? Yes. Because you can shift around these generators, and then hopefully when they start to converge, they will lie close to each other's. But this has not necessarily much to do with the Voronoi cells that are generated always. Sometimes these switch very suddenly. Okay, maybe not if they are close to convergence, I admit that. But when is convergence really achieved? It is not so easy to determine. Yes. When I speak later a little bit more about the PDE, it is easy, because when we have these nodes located on a computational grid, I simply look at the situation when every node sits located on a grid in a new iteration, and when everything does not change anymore, you have convergence. That's it. Yes. So this convergence story appears to be, at first glance, a little bit delicate, at least when you start doing it algorithmically. So now let's have a look at the PDE-based approach. So we have here the Iconal equation, and what you're doing is you compute the Euclidean distance when everything, the underlying density is constant. So at these underlying nodes, you set the distance, the traveling time to 0, and then you compute the distances. And you can generate in some ways the Voronoi cells then from this. Yes. Still, one has to extract the boundary of the Voronoi cells. Yes, but you can do it, and so on. So everything is solvable, more or less. The principal advantage of this is because we are speaking about geodesic distances, you can easily more or less have it as a flexible tool for non-convex geometries and so on, because you simply run your method and the Iconal equation will do what it does, and there is no inherent problem. So this is the advantage. But one needs to address a certain number of questions about it. How high is the accuracy of the scheme that is needed in order to achieve reasonable results? I mean, finally, what one can trust more or less is the geometric approach in this completely, because it delivers something which is exactly exactly constructed. Yes. So when is the situation when we get really something that one can trust with this numerical simulation, and which order of accuracy do we need? And the second thing is, in a practical simulation of this, in order to build the centroidal Voronoi tessellation, which grid resolution do we really need to impose, and what is the impact, and what are the influences? So Many other things that were difficult maybe for the geometric approach are not so difficult for the PDE-based approach, but one has to consider that one needs to make the simulation on probably a very fine grid. So, and this is computationally surely more expensive. So we are testing here two density functions in our small testing environment on the unit square here. And the tests are a very simple, smooth variation here of the Gaussian that you have already seen. And the second one is the Rosenbrock function. It features very strong gradients here at at two corners. So what you expect in Voronoi tessellations that you get with this Rosenbrock density is that you have a valley here in the middle of relatively big cells and some kind of, let's say, clustering of Voronoi cells in these two corners here that are vice versa to this valley. Okay. When you want to evaluate, when we go back to the complete construction, we have an energy minimization problem here. So when we want to evaluate how good a tessellation that is computed is really, what one can do is one can compute the energies here. And see which method gives a lower energy. And this is surely a quality criterion that is reasonable. So the first thing is when we look at the PDE-based story alone about the numerical accuracy. So what we did here is fast marching of first order and second order, just standard methods, as you can take from the book of Thesian, for example. And what you see here on top is from the Rosenbrock function, where you have a certain higher density here. So everything looks reasonable, lower density of Voronoi cells here around. And this is from the Rosenbrock function, where you see here the valleys and a certain higher, let's say, a certain higher density at these corners with a more higher density on the left upper part. So this is what is expected. And you see, okay, you see small differences, but virtually no difference. And when you look at the energies that are plotted here, so we have first and second order. First order is the left column. Second order is the right column here of these Voronoi cells figures. You see virtually no difference. Yes? So the impact of the order is in practice negligible. And so we stick to first order fast marching for our experiments. So now this is the impact of the mesh density. So we put in here, we have two experiments. The first experiment is with 10 seeds for generators. The second series of experiments, I'm sorry, will be with 20 seeds of the generators. And let's have a look at what happens. So to the left is the geometric solution, which is kind of the ground truth that we trust, and we would like to have a similar result with the numerical simulation using the Iconal equation, and we look at a series of mesh refinements. Okay. So on the right, we start here with 100 times 100 grid, then 200 times 200, then 400 times 400. Yes. So for these 10 seeds, we see here that the grid moves, and we see here that the results get more and more identical. So at this, for 10 seeds, 400 times 400 is okay.
Excuse me.
Yes.
You're talking about Cartesian grid, finite different grids, right?
Yes.
So the point xi are not on the nodes of the grids.
For the geometric optimization, generally not. For the PDE-based thing, when we take on Lloyd's algorithm and we relocate, then of course the computed node is usually not on the grid. So we have to do a projection step and we push it to the next grid point. Yes. Okay. These are the more or less ugly details. Yes. Okay. Yes. Okay. Thanks for the question, because it is of some importance, as we will also see in a minute, to speak about these ugly details, yes, unfortunately. Okay, so now let's go over to 20 seed points. One should also say that, okay, no, good, that these Voronoi tessellations are not unique, really. So one can look at the energy, and they depend on the seed points, on the seed point distribution. I should have said that. Okay, so now we go over to the higher number of seed points and have the same grid resolutions. And let's have a look on the right: 100 times 100, 200 times 200, 400 times 400. And still you see, when you look carefully, that the result on the right-hand side is still far away, more or less, from what is considered to be the ground truth. And so the conclusion is, or the implication is, the higher the number of your seed points is, the higher must be the mesh density, yes, which is not a good result for the PDE-based method, because it is a matter of computational time, yes, more or less. Okay, so then now let's have a look at the energies and the performance for the various densities. So left, constant density, so everything is uniform over the whole grid. The results are virtually identical. It is also some part that we have seen at the very beginning of the last experiment. So there's no point to prefer one method about the other from the output point of view. Then if we look at the densities on this 400 times 400 grid for the PDE-based resolution, then we see that there's a certain advantage of the PDE-based method. So this is in this experiment not very impressive. If we consider comparison with some other method here that one of my PhD students, Georg Rado, tried to combine advantages from both method algorithmically and from quality. And then you see that you observe that for the varying densities, especially like Rosenbrock density, the PED-based method has some advantages, and there's a reason. And the reason is more or less the underlying grid. When you have the geometric method, and let's go back just to the very beginning of this investigation. If you want to replace the nodes with the center of mass, you have to evaluate these integrals. If you have no grid, you need to approximate these integrals somehow. When we want to combine of equal order methods or of similar orders methods, then you see that you have just a very simple means at hand to evaluate the integrals if you resort to the geometric method. So you must do something really fancy on the Voronoi cells to get these integrals really related to a high accuracy of the underlying things. You also have to do further interpolation and so on. With the PDE-based method, it is a trivial integration. Yes? And this trivial integration of the density evaluated at some grid points times the grid point location and so on, this already has a reasonable accuracy. So when you have very varying density, in fact, and the grid is able to capture this, the grid-based method is simply much more straightforward and performs at first glance very reasonably well. Yes? So this is the conclusion based on this. Yes? So when you want to make it a flexible tool that can address many functions like, let's say, temperature, stress, whatever you want via this design function rho. It is not much more like this. You need to do a very careful evaluation of these integrals. Okay, so the final conclusion is for us personally, we would like more to resort to the PDE-based method because of higher modeling flexibility, knowing that one has to have a careful look at the underlying grid if one doesn't want to make it too simple and have just the standard Cartesian grid function. But when you do this, it works, and you have a very nice tool that is able to perform some honeycomb-like structures, and you have as a design criterion for the number of material you want to spend, you have the number of seed points, and you have, of course, the density function in order to manipulate. And the idea was, but I cannot show you at this moment results of this, to put it in some loop where you have a finite element simulation of stiffness on n, and you can extract a stiffness function, put it into this, compute a new tessellation, put it again into the finite element solver, and put it into a loop. But I don't have at the moment a result that I can present, as we are not as far. It's really ongoing work. Okay. Now let me give you an idea about the trajectory optimization, because it's easy to spend a whole talk just on this. Yes. But let me a little bit explain what are the difficulties and what you need to do. Yes, and in fact, my explanation is a bit longer, even if it's just a slide more or less. What you want, as I already indicated, is to find the best welding path in terms of the temperature distribution. And now, what does this mean exactly? Yes, because you have, when you want to optimize, you have to put in an optimization objective into the objective function, of course. Yes. So you consider this connected sequence of welding and some dead-heading moves that should be as small as possible. The dead-heading moves were these jumps from one node to the others that I've shown you on the sketch. And what you actually want to minimize is the temperature gradient. Yes. Because when you look at the temperature gradient and at material stress, you can compute expressions for the thermal stress. You can have a look at Young's modulus and all these formula that you have from mechanical engineering, and then you realize that what is good in order to achieve or have the ability to achieve reasonable quality in your output material is that the temperature gradient is best. So we in fact discussed over time several objectives. At first, the first objective some time ago was minimize the highest temperature that appeared. But what really makes sense seems to be to minimize the temperature gradient. So let's have a look at the features of the approach that is already implemented and tested by us, and which appears to work also well. I will show you some results. What do you need to do? So in any of these simulations, when you want to print this kind of hot metal, what you have is the heat conduction within the printed material itself. So let us imagine we print a rod, and we want to understand what is the heat conduction between two parts of the rod. So we make a cross section through it, yes, virtually, yes, not in reality, of course. But we want to have a model across such a cross section. So the heat conduction is proportional to the heat gradient at this cross section. It has to be multiplied by a constant for the heat conductivity of the material, and of course times the cross section exactly there. Yes? So in the total, when you do this consequently, so you have the heat equation. Yes. Which must be tailored to the material that you are using, to the temperatures that you're using, and to the geometry, and you have to solve this. Yes, this is basically the simplest part here, that you have to solve numerically the heat equation. And so that everything works, you should do it in an implicit way. So because when you look at time steps that are important, these time steps depend on the printing process of your machinery and so on. So what you need here is implicit discretization of the heat equation. That's basically no problem. Yes, standard, more or less. Then comes the delicate point. We have seen it also on one slide of the previous talk. You have radiation. So if you print a structure and you imagine two rods that are printed in some geometric location towards each other, they heat each other mutually. Yes. So every drop of metal that you print heats the other drops of metals that you print, and vice versa. So everything is connected, and this is via this radiation. Yes. So, and this is what you have to simulate for basically every step in this printing process, the radiation between the material that is printed. And when you look at the rate of radiation, things get more trivial because it is a power law, first of all. So you have the temperatures, the surface temperatures of the parts that radiate to each others, and they come to the power of 4. Yes? So it is in the terms that you have to discretize and take into account are of higher power. This is also somewhat difficult for the optimization scheme here. And you have to multiply these temperature differences to the power of 4 in order to know the influence of the mutual radiation. It is this difference of these power temperatures. You have to take into account a view factor. I will speak about this in a minute. And you have to multiply this with the corresponding areas that are visible, and you need some further constants like emittivity of how much heat does these surfaces really radiate. And of course, you have the Boltzmann constant that needs to be multiplied with this. So these are the terms that you need to take into account in each time step for the radiation. And when it comes to the view factors, you have things get again a bit delicate because you have to take into account the local geometry and so on. And when you really want to boil it down to something that you can compute, simple models that you find in the literature amount to evaluate numerically a higher dimensional integral. Yes, in our case, in our model, it's 4-dimensional. I guess this is will be standard in these geometrical configurations.
Michael,
yes,
5 minutes, please. If you want to have some time for a question, 5 minutes.
Yes. Okay. Yeah, no problem. Yes. So you have to solve this somehow quasi-Monte Carlo with a quasi-Monte Carlo method. Then you have to model the heat source distribution by the welding torch. It is basically a kind of a heat kernel, but you have to locate it in space and time. And you have material parameters. This was also already a question, and we get this by intensive numerical simulations with Alice Steiner. And after some more approximations, you have obtained a series of mixed integer linear optimization problems, and they are very difficult to solve. So let me show you some results. So we printed this, and on the right-hand side, you will get optimal results from an optimal path, and on the top, and a not so optimal path on the bottom. You remember that the objective was to minimize the temperature gradient. So on top, we have a good result, because when you look somewhat more closely, then you see that the temperature distribution is relatively uniform. At least I can see it on my screen. The numbers here are just evaluation points. So if you look at evaluation points, we can compare here things with a very intensive simulation by Alice Steiner. You see here 3 more sketches. These are different, let's say, model approximations, especially related to the power law. And when we evaluate simply temperature over time computed by our model versus intensive numerical simulation, it looks quite reasonable. What you can also do as a kind of a quality measure is kind of an indirect measure. When you print on the substrate plate, the heat is conducted very quickly from the printed material to the substrate plate. And if you want to consider now something like what kind of material stress has been done inside the material, you can have a look at the material deformation of the substrate plate afterwards, and you can measure it. So what you see here are for 2 of the printing paths, the corresponding plots of the material deformation of the substrate plate. And one can see that we get a much better solution. Okay, very quickly about the second approach, but it is also, I just have a few slides about it. So when you look into image processing and we want to think of doing something for stiffness enhancement, you can compute something that resembles a biological skeleton. And this is the classic medial axis transform. The process is called skeletonization. Yes. So why not try to compute kind of a skeleton for some new structure that needs to be printed? I mean, the idea is somehow appears to be not unnatural. So when you look at the typical examples from skeletonization from image processing, you get something like this here. And this is not very reasonable at first for the purpose, but of course you can modify the account. Yes. Okay, I will not go here into details because of time, but what you do here is again relying on the iconal equation. And then there's a certain idea, it is called Hamilton-Jacobi skeletonization. So we look at the sinks of the rising vector field that you can compute of the distance transform. And the sinks identify more or less, they give a measure for what can be skeleton points. And then you have to invent or take some algorithm that you know well for skeletonization and modify it and remove the points from the structure, from the complete shape in order to get the skeleton. And these are things that you can do with this. So left here, just a box here as a sketch for something that you can do, but in fact you can do any shape. Yes, this is one advantage of it. So on the left here, you see the inner part of the shape, an account of the distance transform. You see the skeleton. You can thicken it by morphological filtering, no problem with 2 tiny structures. And you can fix this together with a boundary. You can apply it in a recursive way. This is here on the right. So you can take the newly computed sequence and apply this thing recursively. Yes.
Michael, please, I'm sorry, but you have to go to the conclusion.
Okay, good. Thanks. So one can also investigate this with some mechanical stress simulation, no problem. And I have just as a conclusion that you find everything in 2 publications recently. And I would just to give you the idea that also these things look very simple. There are many more ideas from 3D vision, just techniques from image processing that are worth to explore also for 3D printing. Yes, and these are not the only ones. It's just that these are very simple. And so many thanks for your attention.
Thank you very much. And sorry for
no problem
putting pressure on you. So hopefully we have some time for 1 or 2 questions. So if you have questions, please raise your hand. Yes, Lorenzo.
Hello. Hi. Thanks for the talk. I wanted to ask if you can give 1 or 2 details on the optimization, the mixed integer optimization that you solve for the scanning path. I'm not sure. Maybe I think either I lost it or you didn't mention.
Very probably I did not mention. It is very intricate, yes. So when I would have to put it on the slides, I would have a very, let's say, ugly slides with tons of formula on
I
it.
guessed.
Yeah. The point is that these models are highly nonlinear, and when you want to, I thought at least it was my attempt to put this to give you an idea what it means. So the most intricate point is the power law, I think, and the radiation. And what you have to do in order to optimize this is to do further approximations. Yes. And you need to linearize the power law. This is the first thing that you can do. You can apply some other approximations. Maybe because of time, I would like to resort here to this first publication here in optimization and engineering. You find all the details, but it is really many pages of approximations and computations before you can really apply the optimization.
So it's not based on anything like I don't know, Dijkstra algorithm for shortest path or maximum fluxes or stuff.
It is
like
a kind of weighted shortest path algorithm.
Okay.
That is true, but you have to put in time-dependent weights on the edges of the path.
Yes. Okay, I see. Thank you.
And yes. Mm-hmm.
Thanks.
Thank you. Maurizio, you raised your hand.
Okay, so can you hear me?
Yes.
Yes. Hi, Maurizio.
Okay. So thank you very much, Michael, for your nice talk and your contribution. I was very curious about the optimization of trajectories. So what is the idea which is behind that? So I can imagine that you can optimize trajectory, but there are a lot of constraints, I guess, with respect to the 3D printing system. So you cannot move the
trajectory optimization?
The trajectory of, I don't know, of the pin that is putting the material on the object. So you are not completely free, I guess. You should respect several constraints in the 3D printer.
I'm not so sure that I could really understand. I think I may have some problems with.
You can move whatever you want.
You mean the Voronoi tessellation, or do you mean the path optimization? I'm sorry.
Yeah, the connection is not very good, I think.
The optimization of trajectory that is done to put the material could be rather difficult to detect because you have also a lot of constraints with respect to the motion of the extruder.
So when it is about the path trajectory optimization, it is basically not a problem. So the path optimization problem is a path planning problem. So you say you have all the parameters that you know from the machine. So this is of course very intricate also. Also to get the material parameters, it is intricate. But then when you have your geometry and you have extracted the graph, it is then more or less, after fixing all these numbers, it is more kind of an abstract mathematical problem. Yeah.
Actually, you're optimizing a path on a graph which is fixed.
Right.
Okay? You're not optimizing the geometry of the path like you would do if you were to print a bulk structure. Here you're printing walls in some sense. So.
Right.
So the trajectory is fixed, and then it's just a purely combinatorial problem, right?
Right.
Okay.
It's in fact a very hard problem, a hard combinatorial problem, and it takes a lot of computation time. So the restriction is at the moment the dimension of this combinatorial optimization problem and computation time, and that's why we also tested several approximations that I was not talking about in detail.
Yeah, let me simply mention that there are other works on the path optimization, but for bulk structure. So really, this is the trajectories that you want to optimize, not only the combinatorial. I mean, Alberto and my team are working on this, for example.
I see.
Okay. Are there any other questions? No other question? So we have a coffee break, a virtual coffee break, but there is a